and sharing my screen. And on my screen, I'd like to start by looking at what we're projecting on the document camera, which are coming dates. Today we're going to look at permutations and combinations and a little bit of an introduction into probability. Homework 6 is due by the end of the day today. That's on that fundamental counting principle that we looked at last class. Homework 7 is on permutations. Actually, I think I'm going to push all of those back to the 24th. I know that was the 17th until I looked at it this afternoon and realized we hadn't done it yet. So I apologize for that. That's getting pushed back to the 24th. Homework, yes.
Homework 6 is due by midnight tonight or tomorrow?
Is the 17th tomorrow? Tomorrow. Okay, hello. Yeah, it's the 17th. Me and calendars, I don't know sometimes. Next class won't be the 24th, it'll be the 23rd. There will be a quiz on the on counting. It'll involve the fundamental counting principle, and then what we're looking at today, permutations and combinations. Before we get started with the permutations and combinations, the screen will be back in a minute. Well, let me wait. Folks are copying it down. I'd like to look at my lab and see if anybody has any questions on the fundamental counting principle that we looked at last class, or on anything from the preceding chapter sets. What we'll do today is we'll do the notes for the first half of, little over half the class. I figured we'll stop somewhere between 7:30 and 7:45, let everybody stretch their legs for a minute, and then we'll get started on the test. So if everybody's done with this screen, does anybody want to, oh, I hate these toolbars, they're always in my way. Does anybody want to look at any homework, either any of the back set assignments or that homework 6 that's due tomorrow on the fundamental counting principle? Do we need to look at any of those? Okay, everybody in the room looks like they're fine. How about you folks at home? Anybody at home want to look at anything from any homework?
I saw one on like the most recent homework that's due tonight, and it has like ends and parentheses and stuff like that, and I'm kind of confused.
Can you remember what question number it was? Ends and parentheses. Let me know when we get to it as I'm scrolling through. I'm not seeing any with ends and parentheses. Can you remember what the question number was? Or can you real quick look at yours and tell me what question number it is? Or is it the homework that I pushed back earlier today, homework 7? I apologize.
I have a question for, it's not for the same homework though. It's for homework number 5.
Okay.
It's it's actually 3 of them. I don't know if you have time for all 3, but maybe one will help with the rest. I couldn't
Okay.
questions on homework 5, number 11, number 17, and number 18. I was completely confused.
Okay, let's look at 17. The person who asked for homework 6 did you find the question number you were wondering about? Not hearing anything while you continue
sorry.
looking. I'm gonna go,
My mute
say that
button.
again?
It was question number 10.
Okay, then let's go back at homework 6, question number 10, and then we'll scoot back to homework 5, question number 17. So question 10 says, you are taking a multiple choice test that has 5 questions. Each of the questions has 5 answer choices and 1 correct answer per question. If you select one of these choices for each question and leave nothing blank, in how many ways can you answer the question? Now, I know when you're doing this at home, in your math lab, the numbers might be different, but it'll be the same type of question. So what I'm going to do is I'm going to minimize this, open the document camera so that I can do the question. Let's try that again. So there's 5 questions, so there's 5 decisions we have to make. For the first question, there are 5 choices for the answer. For the second, there are give me a second. For the second, no. I apologize, the technology is not agreeing with me right now. I am going to, there we go. For the first, there are 5 decisions we're making. For the first one, we have 5 choices. For the second, we have 5 choices. For the third, we have 5 choices. For the fourth, we have 5 choices. For the fifth, we have 5 choices. With me so far? The fundamental counting principle tells me that I'm going to multiply the number of choices that I have for each. So this comes out to be equivalent to 5 to the 5th, multiplying the 5, which means there are 3,125 ways of answering that quiz. So going back to the question at hand, we're saying there are 3,125 ways, and yes, we got it. Any better?
Yeah.
Great. Then let's get out of this one and look at homework 5, question number, we'll take the middle one that you were asking about, question number 17. And people at home, in class, I apologize. You want to see what's on the computer screen. It says that a survey of 125 college students was taken to determine the music styles they liked. Of these, 45 students listened to rock, 44 to classical, 51 to jazz. 29 students listened to rock and jazz, 19 to rock and classical, 28 to classical and jazz. Finally, 15 students listened to all 3 musical styles. Construct a Venn diagram and determine the cardinality for each region. So I'm going to start by making a Venn diagram. Is everybody in agreement that for this Venn diagram, I'm going to need 3 loops?
3. Male over winter.
The first loop will be for rock, the second one for classical,
For summer.
and the third one for jazz. So far, so good. Can you guys in here see that, or is that too tiny?
Yeah, it's like tiny as ever, but I'm like trying to see it as well. But the square box that I put that it's in, it's like a like one.
Is that better?
screen.
I'm going to have to flip back and forth, though, from screen to screen to get to the question.
And then summer. I don't know.
We start in the middle, and the question said there were 15 people who liked all three. After that, we're told that 28 like classical and jazz. Well, classical and jazz is this entire overlap of classical and jazz. That whole region has to have 28. There are 15 in there already, and so we have to subtract and see that we need 13 more people. And in that way, as we fill in that Venn diagram, we have to work our way out. So next, we've got 19 listened to rock and classical. Well, the overlap of rock and classical would be here. That whole region has to contain 19. There are 15 in there already. And so we need 4 more. And I'm guessing that if you were having a problem with this, the problem came from not subtracting as you worked your way out. Last 29 students listened to rock and jazz. Rock and jazz is this overlap. That overlap is supposed to contain 29, but again, there are 15 in there already, so I need 14 more. Then we know that the total for jazz, this entire loop of jazz, that total has to be 51. Well, right now, inside there, we have 14, 15, and 13. So that adds to 29, 30, 42. And somebody check my addition there. Let's see, 14 plus 15 plus 13. Yep. And so when I subtract, I need 9 more in the loop for jazz. Now, I forget who asked this question. Is it making a little bit more sense?
Yeah, it's perfect. I appreciate it.
Do we need to add any more detail, or did you see what you were missing?
No, it's pretty much the same process as everything else. I just didn't. I was very lazy about going about it. That's all.
Yeah, just make sure that as you're filling in your Venn diagram, you subtract what's in there already. Are you okay if we stop here?
Yes, ma'am.
All right, thank you. Is there anybody else who wants to look at anything else before we start with the new stuff? If not, we're going to start looking at our P's and C's. And the first thing that we're going to look at are permutations. And before we look at evaluating permutations, permutations will be the number of arrangements of objects. But in order to be considered a permutation, there are 3 distinct criteria that have to be met. First, the objects have to be distinct. The objects are all different. And so, for example, if I were trying to arrange the students in class, everybody in class is different. Second, I can't repeat. Any object can only be used once. And the third criteria, and this is important for permutations, is that order matters. It's important with a permutation that order matters. So what will these look like? Let's say, for example, I have 4 students. Let's say I have 4 seats. I want to know how many different orders can I sit them. How many different orders can we sit them? Does this fit the bill for permutation? Is each student different? Yes. If I put somebody in one seat, can I reseat them in another seat, or once you're in a seat, you're in the seat? So we can't repeat. And over here, the question tells me that order matters. I want to know how many different orders I can arrange them in. So I'm going to picture these 4 seats. And right now, we could probably figure this out using our fundamental counting principle. First chair I have 4 students to pick from. But now somebody's sitting down. How many people do I have to pick from for the next chair?
I don't get it.
3. Now 2 people are sitting down, so there are 2 left to pick from for the third chair, and then there's only 1 person left to fill in that last seat. And our counting principle tells us to multiply those, and so that would give me 24 ways. Another example, let's say I have a race. In the race, there are 7 runners. In how many ways can they finish?
Is it 7 times 6 times 5 times 4 times 3 times 2 times 1?
Okay, and everybody in the room, did you hear what I got from Zoom? It's 7 times 6 times 5 times 4 times 3 times 2 times 1. The runners are people. Each one is different. You can only cross the finish line once. And if order didn't matter, why the heck are we running the race, right? We always want to see who finishes first. And so when you multiply that out, what are you getting? Anybody doing the multiplication for me? Hopefully you guys all have your calculators with you. And you want your calculator for that quiz next class, because it's going to be a lot of this level of multiplication. So those are examples of permutations. And let's say instead of having 7 runners, I had 20 runners. That multiplication would get annoying fast. And so we want to introduce a new notation. We want to introduce the idea of a factorial. And for a factorial, we're going to say that if n is a natural number, n factorial, that we're going to write n with an exclamation point. And so when you see a number with an exclamation point after it, it's not that we're celebrating that number. It means that we're taking a factorial. Is the product of n and all the natural numbers less than it. We're going to just count down, and then everybody remembers the first natural number is 1. And so we'll count down to 1. If I wanted to write that algebraically, n factorial will be my first number, that will be my first number. Then I'm going to take the number 1 less, n minus 1, the one less than that, n minus 2, and I'm going to keep on going down, down, down until I end up with 2 times 1, decreasing. So, for example, 5 factorial would be, I'd start with 5, and then the number 1 less is 4, 2 less is 3, and I'll keep multiplying by each of the numbers until I get to that smallest natural number, which is 1. And again, I think we've already said that doing that multiplication can be difficult. So I've got 2 calculators with me, 2 different types of calculators, that I'd like to show you how you can get this real easily with your calculator. First of all, I think the model that I had recommended at the beginning of the semester was this Texas Instruments TI-30X, the one with the 2 lines of display. If you have this version of calculator, in order to get that last answer, I'm going to first type in 5. And then I'm going to look at these buttons. We've got the different colored second button. Below that, there's a button log. And next to that, there's another button, PRB. And PRB is a abbreviation for probability. We're going to find a lot of the functions that we need are in there. And so I'm going to press that probability. And do you see, I have several choices. I'm going to arrow over till I get to that exclamation point and press enter. And now do you see I've got 5 factorial. And so when I hit equals 5 factorial, that would multiply out to be 120. Is there anybody who's got this calculator? If you do, please try it and let me know if that's what you get.
Yes, I just did it. I
Yeah.
had the same exact calculator. I got the right answer.
Good. Now, is there anybody who has one of these? Uh-oh. I brought the wrong graphing calculator with me. This one is dead. Its batteries do not work. But I can try. Is there anybody who has a graphing calculator that needs to know how to get to that factorial from a graphing calculator? Anybody at home have one of these? Not hearing that? I'm going to go on the assumption that everybody's okay with just seeing this calculator. There is one exception to this definition. The exception is 0 factorial will always equal 1. That doesn't fit our definition because we're defining factorials just from natural numbers. We need to add a separate case for 0 factorial. So let's have everybody see what you get when you find 10 factorial. Either by calculator or by multiplying 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What are you folks getting for this product?
But like 36,288,000 if I'm not, or hold on, 36 million.
3, 6, 2,
Yeah,
8,
it's
8,
the, yep,
0, 0.
yes.
Okay, I would write the digits and then put the commas in. I think it's
Okay.
3,628,880. You got it right. Just make sure you kind of write your commas in there to give it meaning. So let's say, example, I want to know how many ways can I arrange the letters in the word star? Well, there are 4 letters. They're each different. The arrangements mean the order matters. And so 4 factorial is going to give us
24.
24. What if I ask for arrangements of all the letters in the alphabet? This time that would be 26 factorial. And I'm not going to try to multiply that by hand. When I type that in my calculator, I don't know, is there too much of a reflection or can you folks see this? I'm getting 4.032914611. Wait, that can't be right. There has to be way much more than 4 of them. If you look in the middle, though, on the back, can you see that it has times 10 to the 26th? And so what this set is telling me is this number is way much too big for my calculator, way too many digits, and so it's throwing it into scientific notation. We haven't really talked about scientific notation. Is everybody familiar with the idea of scientific notation?
Yes.
This means that I'm going to take that decimal point and move it, let's see, 26 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, and start filling in zeros. And it should not happen often, but if your calculator throws a number in scientific notation, just be aware of the fact that that might occur. I do believe with the probability project, which is going to deal with a lottery, you will get numbers in scientific notation. Some calculators, instead of putting that times 10 to the 26, some calculators might write that as E26. And so realize if you're expecting a large number and you've got that times 10 to a power or that E, it means you're working with scientific notation. Everybody okay with that? So then we're going to look at more permutations. Let's go back to our race. Our race had 7 runners. And I'm going to be like the Olympics. I just care who I want to know how many ways they can just place first, second, third, get the medals. And so this time, I'm not worried about all 7 places in which they finish. I'm just worried about the first 3. And like before, 7 runners can cross first. After we've got a first place runner, there are 6 possibilities for second place. And then there are 5 possibilities for third place. And so this gives me 210. And this would be an example of 7 permutation race. 7 permutation 3, the first number should be the larger number, and that's the starting factor. And then the smaller number, 3, tells me how many factors. And so I look at that and I fill it in as I need 3 factors, and I'm starting with 7 and counting down. In general, we might see NPR, and the way I learned this a million years ago in pre-calculator days is that it's the product we're multiplying of the first R factors. The smaller number tells me how many factors of N factorial. The larger number tells me what I start with. And so, for example, if I have 15P4, this way I'm taking 4 factors, starting with 15. That would be 15 times 14 times 13 times 12.
What?
Which gives me 32,760. That's the way, when I do it by hand, I fill it in. If you use the Help Me Solve It function in my labs, and I wouldn't be showing you this other than I know this is what Mr. Blitzer shows in the Help Me Solve It. Help Me Solve It in my lab says that NPR is equal to N factorial divided by N minus R in parentheses factorial. And so let's look at that definition with the example we started with 7P3. That would be the first number factorial over the difference of the two numbers, 7 minus 3 factorial. Order of operations, we do what's in the parentheses first. So that's 7 factorial over 7 minus 3 would be 4 factorial. 7 factorial is 7, 6, 5, 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. And you notice the 4, 3, 2, and 1 all cancel out. And so I'm left with that same expression that we had before, 7, 6, 5. 3 factors starting with 7. It's just another way of writing it as a formula. But you folks might be happy to know that you know what? Yeah, let's go here. There's a button for that NPR on your calculator. So let's look at, I think the previous one that we did was 15 was the first number. Can you guys see that on the screen? Yeah, 15. And then I'm going back into that probability. And you notice the first thing that's underlined is NPR. So I'm going to hit NPR, and then I'm going to hit 4. And it gives you the answer. And so those are in that probability menu on your calculator. Don't get too hung up with trying to do it by hand unless you don't have a calculator with you. Then that would be problematic because some of them get to be quite large to do by hand. So before we go too much further with these permutations, there are some questions on the homework that just ask you to deal with factorials. And so if I asked you to evaluate 100 factorial over 98 factorial, I am guessing that when you put this one in your calculator, it's going to tell you overload error. Both of them are way too big for your calculator to deal with. And so with a question like this, if The reason I'm asking is because it goes back to you knowing what that factorial means. 100 factorial means I'm taking 100 times 99
Overflow
times
error.
98, and I'm multiplying all. Hey, guys at home, can you mute yourself if you're not talking to the class, please? Thank you. All the way down to 1. And then in the denominator, 98 factorial would be the product from 98 down to 1. And do you notice that everything 98 and smaller would cancel out? And so this would actually just be 100 times 99, or 9,900. And there is one or two like that on the homework with large numbers. And again, if you try to use your calculator, it's going to tell you overload error because the numbers are just too gosh darn big. But if you go back to that definition of your factorial, the computation should not be tough at all. So just a heads up that you're going to see those in the homework. Now, let's look at another example. Let's say from the 3 people in the classroom today, how many ways can I pick on, be really mean to none of them? So from the 3 of you, in how many ways can I pick nobody? How many ways can I be mean and abusive and tear apart and verbally chastise none of you? Isn't there only one way of doing nothing? And so that's going to be 1. And in general, anything permutation 0 will always equal the number 1 because it's asking how many ways can I pick nothing? And there is only one way of picking nothing.
Excuse me, could you repeat that, please?
Was that a question?
Yes, could you repeat that, please?
Anything permutation 0 will always equal 1 because there's only one way of doing nothing, of picking nobody. There's only one way of choosing 0 things, and so anything permutation 0 will always equal 1.
Thank you.
But now let's go to another type of permutation example. Let's say that we're a director. Let's say we have 10 people audition for 2 different parts. How many ways can we cast them? And I think it's obvious with this one that I've got 10 actors, they're each different. So that criteria is met, they're each different. There's 2 different parts. No one person's going to hold both of them, so I'm not going to repeat. But is it clear to everybody that with this one, because those parts are different, order matters? If I were one of those actors trying out, it would make a big difference to me if I got the leading role or something else. And so here, it doesn't necessarily say order, but because those parts, those positions are different, order matters. And so we've got 10, we're going to pick 2. And so either using your calculator and that permutation function, and I do believe people are using cell phones as calculators, although I prefer you not do that. If you are, I do believe that when you open your calculator, if you turn it into landscape mode sideways, you'll get a scientific calculator, and somewhere on there should be the factorials, the NPR, and a little bit later we'll look at the NCR. Okay, so it's in there. You just kind of have to search. If you want me to help you look at your own personal phone calculator after class, just ask. So that gives me 90. And life is good. I hope. So, next thing we're going to look at, and you're not going to see a lot of these, but it is something you need to be aware of. There are permutations with repetition. And so, let's start with a basic permutation. How many ways can I arrange the letters C, A, T? They're all different. Order matters. If order didn't matter, I probably would have done much better at spelling in my formative years. And we want to use all of them. So there's 3. There will be 3 factorial, or 3 times 2 times 1, or 6 ways. And we could arrange them. C, A, T, C, T, A, C, T, A, T, C, and the C, we need to start with T. It could be T, A, C, or T, C, A. Instead, what if I want to do the same thing with the letters in the word all, A-L-L? Order matters, but they're not all different. We've got 2 L's, 2 are the same. If I try to look at those arrangements, I could have A-L-L. What else could I have? L-A-L and L-L-A. And so here there are only 3. And so what happens is if things repeat, there are fewer. And the way we're going to get that fewer number is by dividing. And so the formula says the number of arrangements of n objects if R repeat, S repeat, T repeat. I'm going to put a dot, dot, dot. Is it's going to be n factorial, what it would be if they were all different. But now I have to divide by R factorial, S factorial, T factorial. And I'm usually, I write that down and people look at it and say it's about as clear as mud. But I think when we look at an example, it clarifies. Let's say I want the arrangements of all the letters in Mississippi, M-I-S-S-I-S-S-I-P-P-I. When I look at Mississippi, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. If they were all different, it would be 11 factorial. But they're not. What are the same? We have 4 i's. So for them, we need to divide by 4 factorial. What other letters repeat? There are 4 s's. So we need a 4 factorial for the s's. And then there are 2 p's. And so I need a 2 factorial for the p's. And we could go through and do this out by hand, but I'm guessing that it would probably be easier for folks to do it with your calculator. But I want to warn you to be careful. It's not written, but when you do something like this, where there's a lot of multiplication in the denominator, you need parentheses around the denominator. Well, they're not shown. When you look at that, you have to see those invisible parentheses there. And so with my calculator to evaluate this, I would go 11, then I'd go into probability and pick my exclamation point. Then I'm going to go divided by, and when I hit divided by, it gives me a slash that looks like the slash in the fraction. But then I need to open parentheses. And then I'm going to have 4 factorial, oops, not random. Let's try that again. 4, I arrowed over too far. Factorial, then 4 factorial, then 2 factorial, and then I'm going to close my parentheses. And when I do that, I get 34,650 ways. Now, if I were to do that without those parentheses, I'm going to go up again, and I'm going to just go through and delete those parentheses. No, I didn't delete the parentheses. I deleted the 4, but that's okay. We can put that back in. And at the end, delete that other parentheses. And without the parentheses, please notice, I get a significantly different answer. The reason it's so different without parentheses is the way this is typed, it's going to take the 11 factorial and divide it by the 4 factorial. And it's only going to divide by the 4 factorial. Then that answer will be multiplied by the next 4 factorial and the 2 factorial. So please, 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 it's going to be real important at the end of the semester when we look at consumer finance. If you've got a fraction with computation, additional computation in the numerator or the denominator, you've got to make peace with that parentheses key, okay? So let's look at one more example. Let's say I have 8 beads. There are 2 red. There are 2 white. And there are 4 blue. How many ways can I arrange them? So if they were all different, there are 8 beads, it would be 8 factorial, but they're not all different. Some are the same. We have 2 red, so we need that 2 factorial. We have 2 white, we need 2 factorial, and we have 4 blue, giving me 4 factorial. And so now could everybody take a minute and evaluate that fraction for me and see what you get. And if you don't have a calculator, I guess you can go through and try to do it by hand. So by hand, I'm getting 420. By calculator, is everybody else getting 420? Remember, if you're doing it by calculator, you've got to put
Yes.
parentheses around the denominator. Okay. And so permutations are those arrangements if order matters.
Did you do the 420 on purpose?
What do you mean? That would be, what is that what you got from your calculator, the 420?
I'm just saying, like, did you do it on purpose? Like that specific number?
No, it was just a random number of beads that I picked.
That's not just a random number.
It isn't. Why not?
420 is a special number to me.
Okay, actually, I'm thinking 420. April 20th is my son's birthday.
It's a special day. That's a special day in
Okay.
your heart.
Yep, that it is. That it is. So going back, we said that for permutations, that's when order matters. If order does not matter, we'll call it a combination. And so combinations are arrangements of, they have to be different, distinct objects. There can't be any repeats, but order does not matter. And if I write NCR, that's going to be the number of combinations. The C stands for combinations of N objects if I choose R of them. In terms of computing NCR, if order does not matter, I'm going to have a smaller number. And so I'm going to find that smaller number by division. NCR is going to be NPR divided by R factorial. Or using that definition for permutations, Mr. Blitzer says that it's N factorial over R factorial N minus R factorial. And if you do it by hand, you might make use of that, but I'm thinking that most people will do it by calculator. So let's look at one example by hand. 5 combination 2. That first definition would be 5 permutation 2 divided by 2 factorial. So in the denominator, I'll have 2 factorial, 2 times 1. In the numerator, I'll have the first 2 factors, starting with 5. And so that would give me 20 over 2, or 10. If I use that other definition, let's see if I can fit this in here. 5 combination 2 would be 5 factorial over 2 factorial, 5 minus 2 factorial. So I would have 5, 4, 3, 2, 1 over 2 factorial, 2 times 1. 5 minus 2 is 3 factorial. And you see, once I reduce, it takes me to the exact same place. I'm guessing that most of you probably won't do that by hand, but rather by calculator. And so, again, I'm going to pull my calculator up here, and I'm going to type in that first number, 5. Again, I'm going to the probability menu, and you notice the first choice was the permutations, the third choice was the factorial, but you see that middle choice is a combination. So I'm going to pick NCR, 5 combination 2 gives me 10. I'm perfectly fine if you use the calculator to do it, but if you're caught without a calculator, please realize that you can still do it by hand. I'd like to have you folks compute a few combinations for me. And so I'd like you to find, oops, I forgot something. So sorry. There is an exception. We'll fit it in here. Anything combination 0 will still equal 1. Anything permutation 0 is 1, anything combination 0 is 1, and 0 factorial is 1. I'm sorry, I forgot that one. So I'd like you to find each of the following combinations. And they're all going to be of the same number, combinations of 6. And so I want 6 combination 0, 6 combination 1, 6 combination 2, 6 combination 3, 6 combination 4, 6 combination 5, and oops, there, that's better. 6 combination 6. And I'm going to be quiet for a minute and ask you folks to just evaluate each of those for me by hand or by calculator, whatever method you have with you right now, and tell me what you get. For the first one, did everybody get 1? For the second one, what did you get?
6.
Yes. Beautiful. For the next one?
15.
Yep. Next one?
20.
20,
Then 6 combination 4 is
15,
6 combination 5 is
6,
6. 6 combination 6 is 1. Did anybody notice anything interesting about those numbers? They, after a certain point, repeat. These are equal. These are equal. These are equal. So 6 combination 0 is equal to 6 combination 6. 6 combination 1 is equal to 6 combination 5. 6 combination 2 is equal to 6 combination 4. And it gives you a shortcut, especially if you're doing it by hand. They each start with the same first number, but you notice over here, for them to be equal, the 2 second numbers have to add to 6. 4 and 2 is 6. 1 and 5 is 6. 0 and 6 add to 6. And so it's the case that n combination r will equal n combination n minus r, the difference between the two numbers. And so, for example, if I wanted to find by hand, and I had 100 combination 98, I'd be looking to divide by 98 factorial. And I'd take 98 factors of 100, which is overwhelming. This rule tells me that that's going to be the same as 100 combination. If I take 100 minus 98, I get 2. And now that's real doable by hand. I want 2 factors starting with 100 over 2 factorial. And so that would give me 50 times 99, which would be 4950. And so it's just a shortcut if you recognize it. If that second number is more than half, it usually is easier to compute if you subtract. Okay?
Can you compute that?
Yeah, I did.
No, I'm saying, can you show that on the calculator?
Oh, sure, on the calculator, you could have just gone with the, turn it on, clear it, 100. And then we're going to go and do combination. And actually, if you're using a calculator, 100 combination 98 you could have done. But it turns out to be the same as 100 combination 2. And doing it by hand, I think it's easier to work with the 2 factors than the 98 factors. So it's not something imperative, but if you're caught without a calculator and have to figure it out, it's a nice trick that sometimes makes your arithmetic a lot easier to do. So then what happens is you've got to decide, do I use a permutation or a combination? And to reach that decision, we have to decide, does order matter? If order matters and the objects are distinct, and there's no repeats, it's going to be a permutation. If order does not matter, the objects are distinct, no repeats, it's going to be a combination. If order matters, but some objects are the same or repeat, that's when we use that n factorial over r factorial, s factorial, t factorial. And so what I handed out in class was a copy of a page from the virtual textbook. And so I'm going to put that up in front of the document camera and zoom an awful lot. And we're just going to try to decide whether we would need a permutation or a combination, and then figure out what the results would be. So looking at the first one on the page, I think that pen is too blotchy for this little piece of paper. It says a medical researcher needs 6 people to test the effectiveness of an experimental drug. If 13 people have volunteered in the test, how many ways can 6 people be selected? So we're picking a group of 6 people. Would it matter to you whether you were the first, second, third, or fourth, fifth, or sixth person picked, or do you just want to be in the group?
Yes, in the
Is
group.
everybody all right? In the group, so order does not matter. It's a combination. So we take 13 combination 6. Next one, question number 44, says 50 people are selected to purchase, 50 people purchase raffle tickets. 3 winning tickets are selected at random. First prize is 1,000, second prize is 500, third prize is 100. And how many ways can the prizes be awarded? So names getting picked out of a raffle. Does it make a difference to you whether your first prize, second prize, or third prize? Yes. And so this time, order matters. It's a permutation, and it would be 50 permutation 3. Are you folks all right if I just set it up and we don't do the combination? Great. Next says, from a club of 20 people, in how many ways can a group of 3 members be selected to attend a conference? Well, there's 20 people, and we want 3 of them. If you were going to the conference, would it matter to you whether you were the first, second, or third picked, or just that you were going?
Just going.
Just going. The order does not matter. That's a combination. Now, I like 46 because it's kind of like a different spin on 44. It says 50 people purchase raffle tickets. 3 winning tickets are selected at random. Each prize is $500. How many ways can the prizes be awarded? Well, if all 3 prizes are the same, does order matter? No. So this one would be a combination. It would be 50 combination 3. Let's skip down to question number 51. Question number 51 says a restaurant lunch special allows customers to choose 2 vegetables from the list: okra, corn, peas, carrots, and squash. How many outcomes are possible if the customer chooses 2 different vegetables? Does order matter? Does it matter to you which order the vegetables get put on your plate?
No.
No. So that'll be a combination. And let's see, there's 1, 2, 3, 4, 5 to pick from. So it'll be 5 combination 2. And I think I had meant to skip down to 53. You have 3 dress shirts, 2 ties, and 2 jackets. You need to select a shirt, a tie, and a jacket for work today. How many outcomes are possible? Is this one a permutation, a combination, or is this like what we did last week? Is this our counting principle?
Say counting.
Counting.
It's our counting principle. We have 3 choices of shirt, we have 2 choices of tie, and we have 2 choices of jacket. So this one is just a fundamental counting principle. Now, I want to skip down to question number 57. And those of you who are at home, I am going to scan this sheet in, so you don't have to worry about necessarily writing them all up. I apologize. I was expecting more people in class and less people at home today. So it says there, oh, I think this shouldn't be 3. I think this should be there. There are 4 Democrats and 5 Republicans on a county commission. From among their group, they need to choose a committee of 2 Democrats and 2 Republicans to examine a proposal to purchase land for a new county park. How many 4-person groups are possible? This is going to take a little bit more writing. First of all, if we're looking at committees, usually if people serve on a committee, order does not matter. So I spent too many years as a stay-at-home mom, and in some ways, some of these combination or permutation questions make me think of all things Cookie Monster. You know how it goes, C is for cookie, C is for combination, C is for committees, C is for cards. All of those will be combinations. So I'm going to use a combination for this committee, but anybody else in the room think we might need 2? I need a combination for my Democrats, and I need another combination for my Republicans. That word "and" in the middle tells me I'm going to use the counting principle and multiply. I have 4 Democrats to pick from, and I want 2. So that's going to give me 4 times 3 over 2 times 1, 6. I have 5 Republicans to pick from, and I want 2. So that's going to be 5 combination 2, which gives me 10. And so now we'll use the counting principle to multiply those and get 60. There aren't that many of those on the homework, but there are some. And just, could everybody see that we really do need 2 combinations, one for the Republicans and one for the Democrats? So, I'm thinking that's probably sufficient from here. It's a little bit better idea, is it a combination or a permutation? Does order matter or not? If so, that takes care of that homework 7, which is all permutations, and 8, which is all combinations. That next homework 9, I'd like to do just a real little bit of introduction into before we call it a day and have you folks take that test. That homework 9, whoops, I should zoom back in a little bit and refocus, deals with probability. And when we look at probability, I'm guessing everybody's heard that word, probability. What's the probability of something occurring? Saying what are the chances of something occurring? It's a measure of the likelihood of something happening. In order to come up with a definition of probability, we need to define some other terms first. And the first is going to be an experiment. And usually, when somebody does an experiment, if you think back to like I have to go way back to the last time I took a lab-based science class. When we did an experiment, we didn't necessarily know what was going to happen. And so in math, when we're looking at probability, we're going to define an experiment as an event with an uncertain outcome. Something that when we do it, we don't necessarily know what the end results will be. So let's look at some examples. One example, classic example, is if I toss a coin. If it's a fair coin, I don't know what I'm going to get. It could be a head or it could be a tail. Another one is I could roll a die. And is everybody familiar with that word die? If you have more than one, they're called dice. But if you have only one, it's considered a die. Die is singular, dice is plural. It's kind of like mouse and mice, die and dice. And then another one is if I pick a card from a deck. At which point I have to apologize. I have on my thumb drive a picture of a deck of cards. I know that back in ancient times, everybody knew what was in the deck of cards. I'm not sure everybody does anymore. And so I will bring with me next class these pictures of a deck of cards so that if you're unfamiliar with a deck of cards, you can, actually see what it is. So is everybody all right? Each of those, when you're asked to do it, you don't know what's going to happen. Then next definition is a sample space. And a sample space is the set, that word sounds familiar, of possible outcomes. And so when I look at my coin, the sample space, what can happen when you toss a coin? Either heads or tails. Are you folks all right if I abbreviate with H and T? Instead, if I look at my die, when you roll a die, what can you get? What are the possible outcomes?
1 through 6.
1, 2, 3, beautiful, 4, 5, 6. And if I look at a deck of cards, and I don't have enough room here for the picture I want to draw, so I'm going to turn the page. When I look at a deck of cards, does anybody know offhand how many cards are in a deck? 52. And they can be broken down by suit. They can be hearts, diamonds, clubs, or spades. The hearts and diamonds are considered the red cards. The clubs and spades are considered the black cards. In each of those suits, you have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. Then there's a king, a queen, a jack, and there's also an ace. I think it's obvious that 2 through 10 in each suit would be considered the number cards. If I had that picture of the deck of cards with me, the king, queen, and jack all have faces on them, so they're my face cards. And the 8 stands alone. The 8 has no face. Then the next definition is that of an event. And the event, an event can be any subset of the sample space. We're all pros at what it means to take the subset of a set. And so if we're going to have E be our event and S be our sample space, we're going to define the probability of an event and the notation that we're going to use is P and then in parentheses E. And we're going to say that the probability of an event is equal to, check this out, N parentheses E over N parentheses S. Now, E and S are both sets. When I look at sets, what does it mean to put that little N in front?
Multiply.
The cardinality, the number of elements. So this is the number of ways the event can occur. Over the total number of events in the sample space. Number of outcomes in the sample space. So let's start with some real simple examples. And from those simple examples, we're going to make a couple of generalizations. And then after we make a couple of generalizations, we'll call it a day with new material and get started on that test. So for my first example, I want to say that I toss a coin. What's the probability that I get a head? Well, we said that the sample space was heads and tails. How many things are in the sample space?
2.
2. And of those 2 things in the sample space, how many are heads?
1.
1. And so that probability will be 1/2. What's the probability of getting a tail?
Wouldn't it be the same thing?
1/2. And is everybody all right? Those are the only possible outcomes. And what's interesting, if I take the sum of them, 1/2 plus 1/2, I get 1. Let's look at another example. Let's say we roll a die. We set our sample space of the numbers 1 through 6. What's the probability that I roll the number 1? How many number 1s are there in that set?
1.
1 out of 6. What's the probability that I roll a 2?
1 out of 6.
1 out of 6. The probability that I roll a 3?
1 out of 6.
The probability that I roll a 4?
1 out of 6.
1 out of 6. The probability that I roll a 5, 1 out of 6. The probability that I roll a 6, 1 out of 6. What's the probability that I roll a 7?
0.
0 out of 6, which is 0. What's the probability that I roll an 8?
0.
0 out of 6, or 0. And can we generalize and say the reason those have a probability of 0 is because they're not possible? And so we'll say that if an event is impossible, its probability is going to be 0. Now, these first 6 are the only possible single outcomes. And if I look at the sum of their probabilities, 1, 6, plus 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 1, 6, doesn't that add to 6, 6, or 1? And so does it make sense that the sum of all the possible probabilities for an event will always add to 1? So the sum of the probabilities of all the possible single outcomes is 1. Now let's look at some events that are made up of more than one outcome. With my die, what's the probability of rolling an even number? How many are even? 1, 2, 3 out of the 6. What's the probability that I get a number greater than 2?
4 out of 6.
Beautiful, 4 out of 6. What's the probability that I get a number less than, let's say less than 10? How many of my outcomes are less than 10?
6.
6 out of 6, which would be 1. What's the probability that I get a number greater than 0? How many of those outcomes are greater than 0?
1. 6 out of 6.
6 out of 6, or 1. These two both have a probability of 1. What do they have in common? Don't you have to get a number under 10? Don't you have to get a number over 0? So we're going to say that if an event must occur, sometimes you hear that it's certain to occur. Its probability is 1. And so then I like to get a little philosophical. Everything in life, doesn't it fall somewhere on a continuum between never happens, totally impossible, or must happen, certain to occur? And so that tells me that the probability of an event is always a number between 0 and 1. Probability will never be smaller than 0. Probability will never be bigger than 1. Probability will always be a value between 0 and 1. Always, always, always. If you do a big, long probability problem and you end up saying that the probability of the event is 17/16, it's wrong because that's bigger than 1. You'll never hit a number bigger than 1. If you do a long, drawn-out probability problem and you end up saying the probability of event is -0.01, it's wrong. It's never negative. Probability is always between 0 and 1. And I'm going to say that over and over and over again, because I guarantee by the time we get to that probability test, there will be some people who give me an answer in the millions. Probability is always 1 or less and always bigger than 0. And I'm looking at the faces of the people in the room with me, and they look like they've kind of had enough of new math for a day, and I don't want to exhaust you too much before I give you guys a test. So shall we stop here and take a 2-minute break and then come back and take that test? People at home, do you want me to show you where you're going to find that test?
Yes.
Okay. And people in the room, do you guys need to stretch your legs first, or you want me to just hand out your papers? Let's give them to you. Okay. You don't have one? Do you need a calculator? I guess I'll let you use your phone this one time. Okay. We have folders, but I don't want to use the calculator. And I have up in my office a box of calculators that I just did not bring with me today. Folks at home, you are going to go into Blackboard. In Blackboard, there's going to be in Learning Modules Content, there's a folder Tests and Quizzes. When I open that folder, there is a place for you to upload your work. You're not going to use that until after you finish the test. Down below that, there's the MAT 106 Exam 1 set. You're going to click on that. It's timed. You're going to click on Begin. And when you click on Begin, you're going to see the questions. If you want to, you can type answers in, but if you don't want to type the answers in, just do them out on a sheet of paper. Some of them, like question 4, has 3 parts. I would prefer that you actually did them on a separate sheet of paper, and you then, after you finish, take those papers that you have, and you can submit them all in the upload work for tests. My favorite way of uploading work for tests is to, at this point, after I finish the test, open Blackboard on my phone, and when I press browse my computer, when I do it on my phone, it allows me to just open my phone camera, and I can take pictures that will go directly into Blackboard. Everybody at home okay?
Yes.
All right, then, oops. I'm going to ask you to get started, and I'm going to stop sharing my screen, and I guess I could ask you to turn on your camera so I could watch you, but, yeah, I'll leave that decision up to you folks, okay? Have fun. It's math. Yay. Thank you, Anthony. At home, if you need anything, I'm going to stop recording.